Problem 158. A gas is contained in a vertical frictionless piston cylinder device. The piston has a mass of 3.2 kg and a cross-sectional area of 35 cm squared. A compressed spring above the piston exerts a force of 150 Newton on the piston. If the atmospheric pressure is 95 kPa, determine the pressure inside the cylinder. Before we solve the problem, let us look at the model that we are going to use. So this is a vertical frictionless piston cylinder device. So if we have this type of model, to determine what the pressure inside this piston cylinder device, we always look at the free body diagram of the piston. If the piston having mass of m, and we know that on top of this piston, the force or the pressure exerted on it is a P atmospheric. And because of the weight of the mass or the piston mass, we are going to have another element of pressure right here, where this is the pressure of the piston. Then, if we like to get what is the pressure, assuming that this piston is at equilibrium, it does not move downward, then we must have another pressure exerted on the bottom part of the piston. So this is P, and we try to get what is P. P is equal to the P for the piston plus the P for the atmospheric. And what is actually P? Actually, P is the pressure of the gas. Okay, so this is the pressure of the gas. So we always look at the free body diagram of the piston in order to get what is the pressure of the gas. So in this case, the pressure that we have here is the P absolute. So in thermodynamic, if we have the value of P without any subscript, okay, or without any gauge written there, or in this case, it's given only P, then this pressure is P absolute. Okay, in this case, it's a P absolute, whereby this is a P from piston, add up with the P for the atmospheric, then we get the P absolute. Okay, but in our case, we are having another element of pressure due to the spring exerted on the top part. So if we can redraw back our model, this is our piston. The piston having a mass, and we have a spring right here. And the spring is giving a force of 150, and we have the P atmospheric exert on the top of the piston side as 95 kPa. Then we have the gas pressure inside here as P, which is equivalent to the P absolute of the gas inside. So this is what been described by this question. Okay. Then if we look at the free body diagram of the piston, we have two type of pressure on top of the piston, which is P because of the spring and P because of the atmospheric, and one downward pressure is because of the P due to the mass of the piston. And then we have to equal or to make the piston not moving, then we have a resultant pressure down here, which is the P, and this P represent the P of the gas. So if you look in terms of the pressure equation, the pressure right here is equal to the pressure because of the spring, the pressure because of the weight of the piston, and the weight of the air, which is represented by the atmospheric pressure. And to look at the individual pressure, this is equal to F divided by A for the piston. Please take note, if this is in Newton, this is in meter squared, then you will get in Pascal. But given the P atmospheric in kilopascal, so you need to divide this by 1000. So then we get in terms of kilopascal. Again, for the piston, P piston is equal to M multiplied by G divided by A. Well, before that, I should remind the A value. What is Pascal? Pascal is basically Newton over meter squared. Okay, we have the Newton right here, the meter squared right here. So the A value, this is our A. A is given in 35 centimeter squared. So you need to get the A in terms of meter squared. So how do you do that? You want to get here meter. We know that 1 meter is equivalent to 100 centimeter. So we want to cancel out the square right here. So this is squared, meaning that we are getting here is 4. So this is squared. So cancel off. Then we have to divide by 10 power of 4 in order to get in meter squared. So please be careful with the units. Okay. And then you know that for P mass of the piston, P is equal to M G divided by A. Right, so we have to divide by 1000 in order to get in kPa. This is in kilogram. This should be in meter over second squared, and this should be in meter squared. Then you divide by 1000 right here, then you get your kPa. Okay. So back to our original question here. Then we could have our model with all the parameters given. So we want to know the pressure of the gas inside the piston cylinder device, our spring, weight of the piston, and if we look at the piston free body diagram, these are all the pressure involved. pressure of the spring, atmospheric pressure, pressure due to the weight of the piston, and the pressure of the gas inside the cylinder, which will be equal to the three element of pressure. So this is our formula used, and this is how if you can do it in a short way, it's up to you. If not, try to do it individually, get the individual pressure, then you sum it up. So this is in the case of kPa for the atmospheric. This is the area we convert, the area of piston converted to meter squared. There you have your factor of 10 minus 4. This is your mass, your G, your force, and everything right here you are getting in Pascal. Then you divide by 1000, then you get kilopascal, then tell it with the atmospheric pressure unit, then you can add it up and you will end up with 147 kilopascal. So that's how you look at a piston in the device, how you determine the pressure inside the pistons in the device. In this case is gas, and please take note that the pressure right here is the absolute pressure, right?